Well, you made it this far, which means I will show you derivative shortcuts. Now, a word about derivative shortcuts. 1. These are the things you're expected to use when you take derivatives. 2. Really, you should take the derivatives this way. 3. Remember the limit definition of the derivative and how it sucked to do all that writing at every step and not forget the limits and all that stuff? You are not expected to use that when you take derivatives. 4. Why then did you put us through that, Kukla? Well, one thing I can guarantee you is that you will be confronted with the limit definition of the derivative on the AP exam. So you do need practice with it. You will see it on the next test. You'll probably see it on our semester final, and you'll definitely see it on the AP exam. Okay? I mean, without that limit, we couldn't do that magic act of taking and finding the slope at a point. So while these shortcuts are going to be nice and very convenient, and I love using them, and I don't want to take a derivative any other way, they completely lose the fact of what it means to do when we're taking a derivative. It becomes a very mechanical process with the shortcuts. It does not connect us to the fact that this function needs to be continuous. This function, the limit of the slopes from both sides of this point must exist. All those good things that we've just learned. So, here are your derivative shortcuts. 1. The derivative of a constant. Okay, so here's a constant, y equals 2. Let's look at the graph of y equals 2. This is y equals 2. What can you tell me about the slope of that line? That's right, it is horizontal. What's the slope of a horizontal line? M equals 0. So, what do we know about the derivative of a constant? The derivative of a constant is always 0. That's it. Just the derivative is always 0. If f of x equals c, I'm going to do a notation here right now. F of x equals c, and I take the derivative with respect to x on both sides. The derivative of this constant is 0. Excellent. Remember, this red form is the imperative verb form. I'm taking the derivative, as opposed to writing dc dx. This is the name of the object. The name of the object is the derivative of c with respect to x. Okay, so that's our first shortcut. Next, and you might have gleaned this one yourself in the last few days. I've sort of hinted at it in the videos. This one is the power rule. So, on the microscope worksheet, you graphed y equals x squared, and then you graphed y prime, and noticed that it was a linear equation. Turns out that it was a linear equation with a slope of 2. And you also looked at y equals x to the third on the microscope worksheet, and you came up with a parabola that was vertically stretched. This is the derivative of that. This is the derivative of that. Tell me how I'm making the derivative. What would be the derivative of y equals x to the n? Well, good job. Y prime would be n times x to the n minus 1. I bring the power down in front. I bring the power down in front. I bring the power down in front. And then what happens to the power? 2 became 1, 3 became 2. This has to become 1 less. So that's our rule for power. If I have, y equals x to the fifth, then I know that y prime is 5x to the fourth. It's that simple. It really does work every time, and I'm really happy it works every time. But I also find it kind of freaky that it works. I mean, you saw that work we did on the microscope worksheet with all those wicked close points and all those slopes, and somehow those slopes were going to make exactly this shape from that graph. It's very cool. Okay, so there's the second rule, power rule. Third, derivative of a constant multiple. What does that mean? Y equals c times f of x. We've got some constant times a function. Like y equals 4x squared, or y equals 2 sine x. We're talking about a number times a function. Okay? So when we have a constant multiple, it's very, very easy for us. We say that y prime is going to be the constant times the derivative of the function. So when I see y equals 4x to the ninth, I know that y prime is going to be that 4 times the derivative with respect to x of x to the ninth. And the derivative of x to the ninth is 9x to the eighth. Now these numbers can be and should be multiplied. There we go. I'm just highlighting the fact that I don't have to take the derivative of this constant. It's just the constant times the derivative of the function. Just the constant times the derivative of the function. Let's write that down. Not that pen. How about this one? The derivative of a constant times a function is the derivative of the function times the constant. Okay, that's rule 3. How about rule 4? Rule 4 is sum and difference. So if I have y equals f of x plus g of x, the derivative is y prime will be f prime of x plus g prime of x. If this is a minus, then this will be a minus. All I have to do is take the derivative of each piece. That's it. That's all that's required here. So, in notation, if I want to take the derivative of f of x plus or minus g of x, that derivative is going to be equal to d of f of x, df dx, that's it, plus or minus dg dx. And so I just take the derivative of each piece. And thus, when we have a polynomial, like x squared plus 3x minus 4, we can put all these derivative rules, these shortcuts, to work for us. So, for example, I know that the derivative of x squared is 2x. I know that the derivative of a constant times a function is going to be the derivative of the function times that constant. And I know the derivative of just a constant is 0. So I know that y prime is 2x plus 3. This is the derivative of that. Okay? So why don't you show me the derivative of y equals negative x to the third plus 5x squared minus 7x plus 2. Please find y prime. Okay, did you get negative 3x squared plus 10x minus 7? If you did, good job. If you didn't, why not? Let me know if you have some questions. Remember, this 3 comes down, multiplies by that negative. I subtract 1 up here. That 2 comes down, 2 times 5 is 10. I subtract 1, I get 1. And the derivative of that linear function is just the slope of that linear function. Or you could say the derivative of a constant times a function is the constant times the derivative of that function, which would be 1. And the derivative of a constant is 0. Okay, so those are the first 4 rules. Now we've got the product rule. This is y equals f of x times g of x. I'm not talking about a constant in a function, I'm talking about 2 functions. And I get it, a constant is a function. And I'll come back and use this rule with you in a few minutes with a constant times a function and tell you why I don't want you to think about that as a function times a function. Okay, so in this case, we're talking about taking the derivative with respect to x of a product of functions of x. Let's say u is a function of x and v is a function of x. Okay, so we're taking this, and the way I can do this is I can actually use my limit definition of the derivative to show you. So what's this going to be? Well, and I'm going to use the general derivative. So it's going to be the limit as h heads to 0 of f of x plus h minus f of x all over h. This is the format that I'm using here. So what will that look like here? It will look like u x plus h times v x plus h minus u of x times v of x all over h. Okay? That seems icky, but sure. Now, I want to do this amazing thing. I want to simultaneously, this is a little bit of math magic, though people with math degrees will say it's just a technique, it's not magic. But, you know, the person who thought to do this the first time, I'm pretty sure that people thought it was magic. So what I want to do is simultaneously subtract and add this u of x plus h times v of x up here on top. Now, because I'm going to be simultaneously adding it and subtracting it, it doesn't have any effect on that statement, except in what it allows me to do. So, I say then the limit as h heads to 0 of u of x plus h, v of x plus h. Now I want to subtract u of x plus h, v of x, and then add u of x plus h times v of x. And don't forget we still have this minus u of x, v of x. Okay? All over h. And you might be saying, Mr. Goodbye, I thought we wanted to make things less complicated, not more complicated. Well, normally we do, except like when we're factoring a trinomial and we get stuck and we use that long method that turns the trinomial into a 4-termed polynomial so we can do factoring by grouping. So too here, I want to consider grouping. I want to look at these two, and I want to look at these two. Okay, so what am I going to be able to do next? Then I'm going to have the limit as h heads to 0, and I notice I can factor out a u of x plus h from both of those. And what will I be left with? I'll be left with this minus this. That's v of x plus h minus v of x all over h. Okay? Now I want to do the same process over here. Okay? So now I'm going to have plus the limit as h heads to 0 of, and what can I factor out of these two? I can factor out a v of x. So I take out my v of x, and I'm left with u of x plus h minus u of x all over h. All right, so what is this? What can we say here? Well, I think I want to break this up one more step. Okay. So here I'm looking at the limit as h heads to 0 of u of x plus h times the limit as h heads to 0 of v of x plus h minus v of x all over h plus the limit as h heads to 0 of v of x times the limit as h heads to 0 of u of x plus h minus u of x all over h. All right, so what do we have here? We have an opportunity to do direct substitution. So if I plug in a 0 for h, I get u of x times, what's this? Now see, if you've been paying attention enough in the last few videos, you'd know that this is the limit definition of the derivative of v. So this is v prime of x. Then we have our plus sign. There's v of x times, and what's this? Well, again, this is the limit definition of the derivative of u. So that's how we take the derivative of a product. U times v. Now, let's be clear about this. I do not want you doing all this limit definition of the derivative stuff. Instead, what I want you to do is memorize this rule. So when I have two functions being multiplied together, oh, and we saw in an earlier video that if y equals sine x, and we took the derivative of that, we got cosine x. Yeah? So let's use that fact now. Ask the question, what if I have y equals x to the third sine x? First thing is, y prime is definitely not 3x squared times cosine x. That is not true. That is very bad. Don't do that. It's not, the derivative of a product is not the product of the derivatives. The derivative of the product is not the product of the derivatives. What is it? Well, it's this. This is our product rule. It says one function times the derivative of the other plus that other function times the derivative of the first. So let's go through and do that with x to the third sine x. Y equals x to the third sine x. Okay, so y prime is going to be the first one times the derivative of the second plus the second one times the derivative of the first. That's the derivative of x to the third sine x. Okay? If we have y equals x to the fifth cosine x, we know that y prime is going to be the first times the derivative of the second plus the second times the derivative of the first. Now, look, see, we could factor these out. And why would I want to factor these out? Because in Chapter 5, we're going to be setting derivatives equal to 0. Chapters 3 and 4, the rest of 3 and almost all of 4, are all about our derivative rules, derivative shortcuts, how to take the derivative. Okay, so that's the product rule. Now, I think I heard someone say, well, Mr. Kukla, this is a product rule. Because I got a function, y equals 2 is a function, and y equals x to the third is a function. Yes, you can use the product rule here. 2 times the derivative of that is 3x squared plus x to the third times what's the derivative of the constant? Always 0. So what are we left with? We're left with y prime is simply 2 times 3x squared. Or the derivative of a constant multiple of a function is going to be that constant times the derivative of the function. Now, I really strongly recommend that you don't think about this as product rule for 2 reasons. 1, it's more work. 2, believe it or not, lots of people get this wrong. And because lots of people get this wrong, I don't want you to do it. I want you just to see when you see 2x to the third or 3 sine x, I want you to say constant times the derivative of that function. You are welcome to use product rule here, but my experience is year after year after year, kids don't do the derivative of the constant properly. And so this doesn't turn out to be 6x to the second like it should be. Okay, so you need to know the product rule. Please make sure you memorize the product rule. And while you're memorizing the product rule, let's take a look at number 6, the quotient rule. So now y equals f of x over g of x. And the proof of this is very, very similar to the proof of the product rule. And what we end up with is if y equals u over v, then, and we take the derivative with respect to x on both sides, we get v times u prime minus u times v prime all over v squared. That's our quotient rule. Remember our product rule, y equals u times v, and then we took the derivative with respect to x of both sides. That was v times u prime plus u times v prime, or it could be written u times v prime plus v times u prime. Okay, it doesn't matter which order we do this because we've got a plus sign. But here, because we have a minus sign, the order matters. The order matters, the order matters, the order matters. And what is the order? Well, Deb Gray, one of my high school calculus teachers, taught me low d high minus high d low over low squared. So this is the high function. This is the low function. So our quotient rule is low, derivative of the high function, minus the high function times d low, the derivative of the function on the bottom, all over low squared. And if you want me to one day, I will certainly show you the derivation of this. But you survived the product rule derivation, and I don't really feel like I need to inflict another, a very similar proof on you again. But if you really want, I'll show you. Okay, so let's take y equals sine x over x to the third. There's our function. And I'd like to know y prime. So I know I'm supposed to take the derivative of both sides with respect to x. Well, what does that look like? Well, Deb Gray says, lo, d high, the derivative of sine is cosine, minus high, sine x, d low, the derivative of this with our power rule is 3x squared, all over low squared. Hey, you know what a lot of people forget to do? They forget to square the low, or sometimes they just forget the whole denominator. Don't forget low squared. You could tidy this up, and certainly this is starting to look like those big GCF factoring problems, and this is why. Those big GCF factoring problems come from us using the product rule or the quotient rule. That's exactly where they come from. And in chapter 5, we have to take these derivatives and set them equal to 0, and so that's why we really want to have the factored form. Okay, so here, just to take this a little further, I might take out an x squared and have x cosine x minus sine x over x to the 6th, and I could do some canceling. Okay, so there's my derivative. You don't need to simplify. You will want to simplify both in chapter 5 and on multiple choice. Multiple choices will often be given to us in a simplified form. Okay, so why don't you show me if y equals negative x to the 4th cosine, no, over cosine x. Yeah. Find y prime, please. Pause the video, give it a try. Okay, welcome back. Did you do low d high minus high d low all over low squared? I did. And of course, you could leave it like this. However, I'm going to tidy this up. I'm going to pull that negative here. Negative times negative times negative is negative. In fact, I'm going to take out a negative x to the 3rd from each term. So then I'm left with cosine x times nothing. Oh, times 4. And then that's a plus times a minus. I take out the minus, I have a plus, x sine x. Then all of this is over cosine squared x. Okay, so that's quotient rule. Now, I kind of want to ask this question. What do I do in a case like this? Sine x times x to the 3rd over cosine x. Well, that's kind of exciting. So, there's a product rule, but there's a quotient rule. So, I'm going to do the quotient rule here with all that stuff as the high function. So, y prime is going to be low d high. Now, d high, in order to take this derivative, I have to use the product rule. This times the derivative of that plus that times the derivative of that. Remember, we're not done. We did low d high minus high d low. The derivative of cosine is negative sine all over low squared. Okay. Yes, you are expected to know how to do that. So again, I used the quotient rule. I said low, d high. When I said d high, I had to take the derivative of this. This is a product of two functions, so I had to use the product rule. The product rule said this times the derivative of that plus that times the derivative of this minus high d low. The derivative of this is this, all over low squared. People often forget the denominator, especially when they're so busy thinking about this. Some people forget all of that part of the problem. Okay, so there's the quotient rule. I got one last derivative rule for you. Number 7, power rule for negative powers. Actually, I want to say not just negative powers, but rational powers. Okay? So now I'm thinking about taking the derivative of y equals x to the 1/2. Well, dy dx will be 1/2 x to the minus 1/2. Or y equals x to the negative 4th. So y prime is going to be negative 4x to the negative 5th. So what if I have y equals x to the n power? What will the derivative be? That's right, n times x to the n minus 1. This power rule that we talked about before works not only on whole number values, like y equals x squared becomes y prime equals 2x, but it also works with negative exponents, it also works with rational exponents. I can always use that power rule. Bring the power down in front, bring the power down in front, and subtract 1 from the power. Subtract 1. This does not become negative 3. This becomes negative 5. Okay? All right, so those are our derivative shortcuts. Let's practice them. Please find f prime of x in each case. Okay, 1. 3x squared minus 2 over x plus 5 over x squared equals f of x. So find f prime of x for me. Oh, you're not sure what to do with those? Well, hold on. I thought we learned in Algebra 2 that 1 over x was x to the minus 1, and that 1 over x squared was x to the minus 2. See, it may be helpful to take these and turn them into these, because the derivative, 6x plus 2x to the minus 2 minus 10x to the minus 3. So I brought that down, which is why this is now a plus. 1 times 2 is 2, and I subtracted 1. Negative 1 minus 1 is negative 2. I brought down the negative 2. Negative 2 times 5 is negative 10. I subtracted 1 and got negative 3. All right, so there's y prime, or f prime. Number 2. X squared minus 2. Oops, I'm supposed to say f of x equals x squared minus 2, x to the minus 1 plus 1. Okay, please take the derivative here. Come back when you're done. Welcome back. So this is a product rule situation. I have a function times a function. So f prime is going to be this times the derivative of this. Now the derivative of this is negative 1x to the minus 2, and the derivative of a constant is 0, plus this times the derivative of that. The derivative of a constant is 0. So that's my derivative of this. But you know, there's a second way to do this derivative, and I want to show it to you. This is f of x. F of x equals x squared minus 2, x to the minus 1 plus 1. So what if we do a little algebra here and turn this into x, because I'm multiplying these, 2 plus negative 1 is 1, minus 2x to the minus 1, plus x squared minus 2. This is f. Well, great, I FOILed it out, and now I just take the derivative of each piece. 1 plus 2x to the minus 2 plus 2x, derivative of a constant is 0. Yeah. This should be that. They should be the same thing. In fact, we could take some time to distribute and combine like terms to get us to here, but we don't have to. Now, I want to say something about this approach. Students who are first learning these derivative shortcuts, they love FOILing it out and then taking the derivative of each piece. And they aren't so keen on using the product rule. However, when you have a situation like y equals sine x times cosine x, you're not going to be able to FOIL that. There won't be any distributing. And so you're gonna have to do the product rule. And I'm going to tell you right now, you're gonna have to do the product rule a ton. And you're gonna have to do the quotient rule a ton. So you might as well practice those. Because this idea of when I have y equals x squared plus x times 3x minus 4x squared, and you think, okay, that's going to be 3x to the third plus 3x squared minus 4x to the fourth minus, 4x to the third, and then I'll take the derivative of each piece, 9x squared plus 6x minus 16x to the third minus 12x squared, and then maybe combine like terms. But that is going to be so uncommon. It may be that you see it in tonight's homework, but really, I would think about using the product rule. This times the derivative of that, plus that times the derivative of that. And so we get negative sine squared x plus cosine squared x, which is not our Pythagorean identity, but it's kind of close. Actually, I think it's a double angle identity. All right, so how about this one? Number 3. F of x equals 3x to the fourth minus 2x to the third plus 4 over 2x squared. Okay, so I see a quotient, so I'm going to use the quotient rule. F prime of x is going to be low d high, the derivative of this, 12x to the third minus, bring down the 3 times 2 is 6x squared, and the derivative of 4, a constant, is 0. So low d high minus high, 3x to the fourth minus 2x squared plus 4, d low. What's the derivative here? Well, this is a constant times a function. The derivative of the function would be, bring that power down, 2x times the constant. So we've got 4x over here. All over low squared. So that's one way to do this problem, and that's using the quotient rule. Now, there is another way to do this problem, and like that other way of doing that problem so I didn't have to do the product rule, I could split this up into 3 fractions. And so now f of x is 3x to the fourth over 2x squared minus 2x to the third over 2x squared plus 4 over 2x squared. And so I could simplify each of these and say that 3 halves x squared minus x plus 2x to the minus 2. Oh, that's so easy to take the derivative of. f prime would be 3x minus 1 minus 4x to the minus 3. Okay? That was a lot faster than the quotient rule. I gotcha. I know. You won't be able to do this very often. You will see it in tonight's homework, but once we start learning the derivatives for more functions, we're not going to be in this happy polynomial place that allows us to use these alternatives. You're welcome to use these alternatives while you can, but I really need you to be ready for when you see ln of x times tangent x over secant inverse x, where, plus, yeah, splitting these up, not going to help you in any way, shape, or form. You're just going to have to use the quotient rule. So please make sure you know the quotient rule. Please make sure you use the product rule. Okay, how about this one? F of x equals x to the minus 1 plus 2 times x to the minus 2 plus 1. Please find f prime of x for me. Okay, did you use the product rule because you saw a thing times a thing? If you did, you might have said this times the derivative of that. The derivative of this is going to be minus 2x to the minus 3. The derivative of a constant is 0. Since we're doing product rule, I now have plus this, x to the minus 2 plus 1, times the derivative of that, which is going to be negative 1x to the minus 2, and the derivative of a constant is 0. I would not bother to tidy this up at this point, but in Chapter 5, we have to set derivatives equal to 0. And so I would think about factoring out the lowest power of x from both of these. We'd probably take out a negative as well. Okay, how about this one? F of x equals x plus 1 over x. Please use the quotient rule. Okay, so this is going to be low d high minus high d low over low squared, which is going to be x minus 1 over x squared, or negative 1 over x squared. I think I did that right. That went very fast. Yeah. I agree. You could also split this up into x over x plus 1 over x, and then you could take the derivative of this, and the derivative of this is going to be 1. And remember, this is x to the minus 1, so minus 1x to the minus 2, which is 1 minus 1 over x squared. Well, wait a minute. I've got the minus 1 over x squared, but I don't have a 1 minus. Did I miss something here? Well, let's see. Low d high minus high d low all over low squared. And so that gives me x minus 1 over x squared. These canceled, leaving me that. So what happened up here? I split this up into 2. Oh, silly me. So this is the function, right? 1 plus x to the minus 1. But now I take the derivative of that function. The derivative of 1 is 0. And the derivative of this would be minus 1x to the minus 2, or negative 1 over x squared. See, we do get the same. Okay, good. So, what could you do with this one? F of x equals x to the minus 1 plus x to the minus 2 over x to the minus 3. Now, some people like getting rid of the negative exponents. But the problem is, inevitably, that student does this. Oops, that's plus x plus that. And that is really bad algebra. Because really what I've got here is f of x equals 1 over x plus 1 over x squared over 1 over x to the third. If I make a common denominator here, I've got x plus 1 over x squared over 1 over x to the third. So that's going to give me x plus 1 times x to the third over x squared. And then I could do some canceling. I've got x times x plus 1, which is x squared plus x. Now, if you do get through all of that, yeah, taking the derivative here is wicked easy. It's just 2x plus 1. But most students do something like this, where they just move this to the bottom and move that to the top, and that's wrong. So don't do that. You can do this if you want, or why not just use the quotient rule? So the quotient rule, remember, says low d high. The derivative of this, let's start here, is negative 1x to the minus 2. And then the derivative of this is minus 2x to the minus 3 minus, right, we did low d high. Now we need minus high d low. The derivative of this is minus 3x to the minus 4, and all of that over x to the minus 3 squared. All right, so there's our derivative using the quotient rule. And I know that you're saying, that's much uglier than what you did before with the complex fraction and all the algebra. I want to do that instead. Sure, and that's nice to do instead, except most of calculus class will not give us the opportunity. So maybe I should say, yeah, why don't you do that now while you can? But really I want to say, please don't do that, because what's going to happen is you're not going to know how to use the product rule when it comes time to know how to use the product rule. All right, so there we have our first day of derivative shortcuts for you. I hope this was helpful. I notice that homework is bookwork, and that homework is bookwork, and you should be able to get through it pretty easily. It looks like it's only 15 simple derivatives. All right, I'll see you more in the next video for assignment 40, where we're pretty much just practicing these 7 rules. All right, take care, everyone. Have a great day.